Since 1945, the von Neumann architecture has defined how machines process data. It runs on a flat sequence of binary digits and Boolean logic gates. This achieves universal computation, but it does so by stripping away the topological and geometric structure native to the information. When a 120-bit datum enters a modern CPU, the machine flattens it into a one-dimensional linear string of ones and zeros. To reconstruct the meaning that this flattening process destroys, classical computers rely on complex software abstraction layers. These layers are fragile and highly susceptible to errors. Zylatic cyclotoral processing, or XCTP, assigns every datum to a discrete physical coordinate permanently positioned on an 8-dimensional geometric lattice. Storing data as a spatial position removes the need for software abstraction. The architecture insulates the information from systemic errors by housing it in exact structural geometry. To bring standard data into this environment without flattening it, the system uses a specific entry vector, the base 240 legacy bridge codec. As standard binary data hits this bridge, every block of 15 bytes, or 120 bits, is losslessly expanded into 16 base 240 integers. These 16 integers map directly onto the 240 discrete roots of the E8 constellation geometry. That 16th coordinate holds the topological and structural context that a flat binary system normally discards. Expanding 15 bytes into 16 lattice coordinates provides the precise density required for legacy data to survive intact inside a structural computing space. We know this mapping perfectly conserves the original entropy because of the information conservation identity. Every single root among those 240 coordinates carries precisely 7.907 bits of data. This chart demonstrates exactly how that information is decomposed. The base bar represents the binary layer, accounting for exactly 1.0 bit. This defines whether the coordinate structure is classical, integer-based, or quantum, half-integer-based. The century layer stacks on top of that, adding 2.585 bits. This layer dictates the coordinate's vector alignment across 6 specific quaternion axes. The octanonic layer locks in the final 5.401 bits. This gives the absolute exact fine position of the data within the 240 root framework, bringing the total exactly to 7.907 bits and leaving a residual variance of 0. With 0 unexplained variance, the E8 lattice functions as a naturally occurring latent variable model for information storage. To execute operations on this data, XCTP projects the E8 roots onto a flat mathematical surface called the Clifford torus. The torus contains 24 discrete positions. Processing a calculation means taking a coordinate and physically rotating it across this surface. These rotations are driven by 3 Galois involutions called Lipps operators. The L5 cascade instantly resolves 7/8 of the toral volume, splitting classical D8 roots from quantum S+ roots. Then, the L7 boundary resolver bisects the remaining 1/8, targeting the Heegaard boundary between data types. Finally, the L35 operator executes a complete Galois decomposition to verify the exact structural position. Computation in this architecture involves 0 calculation of numerical values. Processing is exclusively the act of rotating geometric coordinates until they lock into absolute mathematical truth. Complex operations require scaling beyond a single 8-dimensional space. The architecture expands vertically using the paired prime tower of BABEL. Level 0 operates within the 8-dimensional E8 lattice via primes 3 and 5. Level 1 expands to 24 dimensions using the Leech lattice and primes 5 and 7. Finally, Level 2 scales into the 120-dimensional Craig lattice.
This expansion reaches a strict limit at a prime recurrence terminus of 1321, creating a boundary known as the Mobius fold. Instead of expanding outward, the 120-dimensional peak uses an involution to fold back inward. It plunges its geometry directly back into the 8-dimensional base. By topologically looping the lattice through itself, the system traps data inside a self-contained computational universe, completely removing the need for external memory calls. Standard 21st-century silicon hardware cannot natively house a 120-dimensional toral geometry. To bridge this gap, Layer 1 of the architecture introduces the chiral nested trilateral architecture, or CNTA. It emulates the quantum environment using classical components. The engine relies on stereoscopic measurement. 2 observation engines, alpha tracking positive chirality and beta tracking negative, independently monitor phases across shared hardware conductors. If they disagree, the third gamma arbiter tower activates, stepping up one dimension level to force a consensus. The hardware scales by translating classical RISC instructions into fractional phases. This allows the system to holographically nest up to 14,400 simultaneous emulated qubits. This trilateral stereoscopic mechanism maps theoretical 120-dimensional mathematics directly onto functional physical server racks. This entire framework culminates in the final application layer, the Zennoran operating system stack. The execution hierarchy is linear. Layer 3 interfaces call Layer 2 cognitive engines, triggering Layer 1 CNTA hardware, all controlled by Layer 0 Toral mathematics. Data flows downward into exact algebraic integers. Upper software abstractions cannot corrupt the underlying structural geometry. Because of this isolation, the cognitive engines process semantic intent without using neural networks, probabilistic weights, or statistical guessing. Complex machine logic and meaning emerge entirely from precise topological search and absolute structural coherence. Instead of traditional RAM, Zennoran OS relies on a structural long-term memory protocol called the chronostamen. As the system processes data, phase tension physically accumulates and leaks into the lattice architecture. When tension hits a threshold, a sleep consolidation mechanic triggers. The system spontaneously emits a corrective rotation, disintegrating unstable geometries, leaving only perfect palindromic loops. The final line of defense is the 0.053 convexity gap, a strict mathematical limit derived directly from golden ratio constants. Hallucination filtering relies on this gap to operate with 100% determinism. If the cognitive engine attempts to output a coordinate that falls into the 0.053 gap, it physically cannot exist in the constellation. The structure deletes it automatically. Inside this framework, an execution error or hallucination is not a fixable software bug. It is a geometric impossibility that the architecture refuses to house. Computing is evolving from flat, fragile von Neumann binary arrays into a multidimensional, self-correcting toral continuum. Modern AI neural networks rely on statistical probabilities. The E8 coordinate grid replaces that ambiguity with absolute structural certainty. This technology provides the blueprint for quantum analog processing and advanced decryption without requiring physically unstable quantum hardware. The system's ECDLP solver is already targeting the 135-bit cryptographic frontier, pushing past the recognized limits of classical search algorithms. The future isn't about teaching machines to process numbers faster. The solution lies in providing an immutable